Right, so let's just first look at some data. The return of stock versus bond in the United States from 1926 to 2003 or 2004. All right, so let's take a look at the data. What do you see? The blue line is real stock index, right? So adjust for inflation. The purple line is the return of government bonds, right? The U.S. Treasury bonds are widely regarded as the risk-free asset, right? No one thinks the U.S. government is going to default. So once again, this is inflation adjusted. And what do you see? It's in which one has higher return? Stock, right? I mean, there's no contest that stock has a higher return. Okay, another way of looking at that at the same data is look at what we call the equity premium. So that's basically that's S. That's S. The difference between stock return and risk-free return. That's equity premium. Right. So for a 20-year investment period, right, from 1944 to the year 2000, right? Take a look at the difference between stock return and bond return. One thing you notice is, since the end of the Second World War, it has never been a year in which the stock would give you a lower return if you invest for 20 years. Now that's something very important. We will come back to that later on. We are talking about long-term investment here. We're not talking about like day trading or even trading for just buy and hold for a few months. We're talking about a 20-year investment period, right? So buy at 1924, sell at 1944. Yeah, that's what we're talking about. Yeah. Yeah.
This is annualized.
This is annualized. Yeah, it's average equity risk premium in percent. Yeah, it's annualized. It's annualized. Right. Now, some of the worst case you can do. Now, when are worst? Now, there are some cases that read that. This one, 4, 5, 6, 7. This is basically what happens if you. So initially the returns are low because of the Great Depression. The returns are low in here because of the oil prices, right? And the financial meltdown that associates with that, right? So there are periods of low return. This is pretty low because you're just getting like 1% return, right? Even after investing for 20 years, you're getting a low return, right? So, okay, so now, but in any case, you never lose money investing stock for the long term. That's what this diagram wants to say. Is that if you hold stocks long enough, you're never going to be worse off than if you just put money in your bank, right? So that's what this is. Okay. Now, given this fact that holding stocks for long term, it's never going to be worse than holding a safe asset, right? What would you expect people to do when they are saving for retirement, for example?
Early on in their career, then they should put them in stocks.
Right. So one thing this implies that there's very little reason why you should invest in safe assets for retirement when you're young, right? Because if retirement investment is money that you're not going to use for many years, right? And from this we can see that it's highly unlikely that you can lose money over that long period of investment. So people should invest in stock. That's what it says, right? People should invest in stock. If the money you have you're going to save, then you should invest in stock, right? Right now. Okay, so for simplicity, I'm going to assume the average U.S. investor has CARE utility and normalized wealth to 1. Now, this is not exactly correct, but I mean, for demonstration, I want to make it simple. So let's just consider this case. CARE utility, wealth is 1, right? Because that makes the math very easy to calculate. Now, CRA utility is this one, right? And the solution is the money in stock equals to excess return over A times the variance of stock return. So now average excess return of stock is around 7% per annum, right? So that means if the risk-free asset, which is U.S. Treasury bonds, give you 3% return this year, you can expect the stock market to give you something around 10% return, right? Standard deviation around 50%, right? Standard deviation in a typical year is higher than the return, right? Which that makes it risky. Now, assuming that the U.S. investors have 30% of their wealth in stock, which is definitely higher than reality. People do not have 30% of their wealth in stocks. Yeah, they don't. Then, simple calculation, because I've normalized wealth to 1, then 30% of wealth is 0.3. So, the excess return of stock of a bond or over risk-free asset is 0.7. We're trying to figure out what A is. So this is the risk, standard deviation, 0.15. You get an estimated. Per risk aversion of 10. Okay, so this is a overly simplistic calculation, obviously, but it's the same idea. Like you can use more realistic numbers, you will still get something like that. Right? Is that the parameter A is going to be something quite big, like 10. How big is it? How big is it? So absolute risk aversion of 10 implies the following. Imagine we offer the investor the choice of getting an additional 50% of her current wealth for sure. So I'm saying, okay, how much money do you have? I'm going to give you 50% more. Versus, now it's a very weird example, it's somewhat hypothetical, but the second choice is 99% chance of getting X% more and 1% chance of losing 1% of your current wealth, right? So one choice. So now we're asking the individual to choose between two choose between two outcomes. One is risk-free, the first one. I give you 50% more of your wealth, no question asked, right? If you have $10,000, I'll give you 5,000 more, right? That's it, no question asked. The second choice is risky, but it's in some sense very low risk, right? There's a 99% chance of getting something more and 1% chance of losing 1% of your wealth. So the downside is only $100. 1% of losing $100 if your wealth is $10,000, right? So how large does X has to be to induce the individual to choose the second option if A is as high as 10? Now, you can see that you would imagine realistically, if X is high enough, pretty much everyone would take that option, right? If I'm offering you 100% more, right? I'm offering 100% more 99% of the time, and you lose is 1% with 1% chance. That seems like a good deal, right? So you think that realistically people would take this deal. If you do the calculation, right? So left-hand side, 1.5%, 1.5 times the wealth for sure, versus in the right-hand side, 99% chance, more money. 1% chance, slightly less money. Fit in the CARA utility with a parameter of 10, right? And then you solve. You find that it's actually impossible to come up with any X that would satisfy the equation. That's how risk averse with a absolute risk aversion of 10 is. It's unrealistically
risk averse. That's what it is. Realistic values of absolute risk aversion is somewhere around 1 or 2, not 10. So this is a complete. So if you have a risk aversion as high as 10, you're really risk averse. Even 1% chance of losing 1% of your wealth is unacceptable to you. Right. Okay, so that's the problem, right? That's the problem. The problem is, it's like, now if people are really that risk averse, then they would always choose the safe option if we offered infinite wealth. Now the real problem here is that, so the math, you can think about it at home. It's very simple. It's a very simple calculation. So the problem is that people seems to be, if you given the actual investment pattern, they seem to be very risk averse. And it's not just a problem of CARA utility. Now with CRRA utility, it's harder. The calculation is harder, but fortunately someone has already done it. Prescott, who won the Nobel Prize. He has this paper in 1985 called the Equity Premium Puzzle, which is exactly about the topic we are covering now. Is that, well, okay, stock market gives you a high return, safe option gives you a low return. How come people are not investing more in stocks? Now, what this diagram says, you can see how old this paper is, right? 1985, because the diagram is hand drawn, right? It's hand drawn. He has pretty good handwriting though. So
I thought it's special font.
No, it's hand drawn. It's 1985. I'm not even sure he's a computer in his office, right? So what it says is this. Now, on the horizontal axis is risk-free rate. On the vertical axis is risk premium, which is equity premium. It's the same name for excess return, equity premium, risk premium. They all mean the same thing. That is the difference between stock return and say asset return, right? Basically, what it says is this. Now, given realistic level of risk aversion that we observe in other places, in other sources, right? You can ask people to do an experiment, do some small, see what they choose in scenarios that are well controlled, and see how risk averse they are. Given what we think is realistic amount of risk aversion, Prescott's calculation suggests that at most the excess return of stock over bonds should be like less than 1%. This 1%, right? So it's the admissible region, given what we think is realistic risk aversion, is very small. The reason is, once again, remember the second diagram I've shown you. If you invest long enough, stock return is always positive over bonds, right? So it's sure gain. You can kind of see that as an arbitrage. Over 20 years period, buying stock over bond looks like an arbitrage. Then you should always go for stock, right? So which is why the admissible region is so small. Because in economics, we think arbitrage should not really exist, right? You shouldn't have a situation where option A gives you higher return, option B gives you lower return, and somehow this persists forever, right? Right? In economics, we think that if option A gives you higher return, option B gives you lower return, always, then everyone will go for option A. And then that would push up the price of option A, right? And make the return lower. But that's not happening. That's not happening. Year after year, stock gives you 7% higher return on average. Why aren't people buying stocks? So this is what we call the equity premium puzzle. Is that existing investment pattern suggests an implausibly large rate of risk aversion. People must be really risk averse if they are not investing in stocks, even though stock gives you much higher return than bonds. Even if you now, how long do you have to invest in order for this to be safe enough? 20 years, very safe. 10 years is 99% safe, basically. 5 years is only about half safe, though, right? So we're talking about something about investing for a decade. If you go down to 5 years, then it's only already half and half, right? Because if you think about it, we basically have sort of
sort of a financial crisis once every decade, so right. So whenever you have a financial crisis, then the stock return would plummet. So if you invest for 5 years, it's not long enough for you to recover in those cases, right? So 10 years or above is 99% safe, and plenty of people have money in their bank for over a decade. Right?
I can understand the positive, but I can't understand the graph from the earlier side.
Which one? The previous one?
Hand-drawn graph.
The hand-drawn graph. What it says is what is done is this. Now the bad thing about PowerPoint is that when I'm recording, it can't go back. But I can draw a diagram here. Now what the diagram says is, okay, this is risk-free return. Okay. Now this is the risk premium. So this is how much stock return is higher, right? This number is not going to be negative because stock is risky, however little. So this has to be at least, this should be positive, right? The thing is, if I'm risk neutral, then this should be exactly 0, right? If they can have the same, because if I'm risk neutral, I don't care about risk. So as long as the two options have the same average outcome, I'm fine. So if I'm risk neutral, risk premium will be 0 always. If I'm risk averse, this number should be positive, slightly positive, right? So this diagram shows is that based on the model they have, this number should be less than 1%. So that's why they have something like this, right? This region is fine. So given that you're not really risk averse, then you would be willing to buy stocks if there's a slightly higher return to compensate for the risk, because the risk is so low in the long run. That's what I just want to say. Now, a question is why doesn't actually extend all the way to here. That depends on the specific model they are using, the CRA. So the CRA model. But the idea is that stock is quite safe over the long run. So as an investor who is not too risk averse, you would be willing to accept a slight premium to hold stocks. There shouldn't be a requirement to have an enormous difference in return. That's what I'm trying to say.
Premium here, it means
the additional return you get from stock over bonds.
So even if it's very small, people should still invest in stocks.
So yeah, all you need to do is let's say bond gives you 3%. All you need is something like 4%, and people should invest in stock over bonds. That's what it says. All right. So the question really, so the equity premium puzzle is one way to put it is to say that people are not investing. Well, right. So these two are the same thing. What you can either say they seem to be implausibly risk averse, or you can say somehow people are not investing. Right? Somehow people are investing too little. Why might be the reason? Right? That's something we want to explore. All right, so we're going to take a break now. We're going to come back in 15 minutes. And okay, so now, why might we be seeing such a low level of investment? Now, one possibility is that we might not be observing everyone's wealth, especially those who are not investing in stock at all, right? Our accounting might not be accurate. For example, let's say if only half the population is investing in the stock market, then the proportion of wealth in stock is 60% of those who invest in the stock market rather than 30%, right? Now, you still need to explain why half the population is not observed, but if that's the case, if you're not observing everyone, then you would be underestimating the proportion of wealth in the stock market. But then you really need a lot of unaccounted wealth to make that happen, right? Because now let's say in this case where we're observing only half the people, then A is only 5 instead of 10, right? So, but as I have mentioned, a reasonable ARA and reasonable absolute rate of risk aversion is 1. So you need really high number of people not being observed for that to work. So typically, I don't think that's a reason. Like, no, I don't think anyone thinks that's a reason. There are multiple reasons multiple theories to try to explain the equity premium puzzle. Now, today we're going to talk about one of them, uh, the one that is most important to behavioral economics. Okay, so now let's take a look at this diagram again. This is the diagram that I used to explain to you why investing in stock is a good idea over the long run. And I think this is pretty convincing. Like you pretty much, you literally always come out on top if you buy stocks over bonds. But this is probably not the diagram people have in mind when they consider investing in stocks. This diagram might be more realistic in terms of what they have in mind. So this is the return from investing only for a year, right? Okay, once again, so the data is the same range, right? So we are starting from 1920s because now we're looking at yearly returns, right? You can see that if you look at the yearly return, it almost looks like it's half and half, right? Half the time you earn money over bonds. Half the time you lose money over bonds. So if you look at a yearly return, stock market suddenly becomes a lot more risky. Half the time you gain, half the time you lose it. Right? So that looks very risky. The fact that over time the gains compound, right, canceling out the risk, is lost in this representation. Right? You can't see that in this diagram. All you can see is that half the time you are gaining money, half the time you're losing money. So another possibility is that investors don't think in the way expected utility requires them to. Expected utility says that, well, you're considering the final outcome and you're thinking about which one gives you a better deal. Well, maybe that's not how people work. What if people are short-sighted, so they only consider short-term gains and losses? They actually do not see 20 years return, or they can't imagine what it's like to invest for 20 years. Instead, they focus on annual performance. Now, there are a lot of good reasons to think why that's the case. Besides psychology, there's also the fact that most of the time when you look at stock charts, they show you relatively short durations, right? When you read stock recommendations and commentaries, they're usually about short-term performance. So the information people receive are mostly short-term. Second, what if for most people making a loss is more painful than not making an equivalent gain? In some sense, this is another form of risk aversion, you can say, right? But I don't want to make a loss. Like one gain, one loss, I'm still coming out worse off. Like I'd rather not have any gain, not have any loss, versus one gain and one loss, right? That's what we're saying. Now, this idea that people are short-sighted and they really hate losing, it's called myopic loss aversion, right? So myopic refers to short-sightedness, and loss aversion refers to the hate of loss. This idea is it's proposed by Richard Thaler, who won the Nobel Prize last year. Okay, so in the eyes of myopic loss-averse investors, the stock market is really undesirable because, well, first, they only look at short-term. And I've shown you, if you look at the short-term returns, it looks very risky, half up, half down. And they're very risk-averse because they really don't like losing money. They would definitely prefer not having to face gains and losses so frequently, right? I'd rather just stay safe. This is called myopic loss aversion. Okay, so I've explained why would we think of consumers are myopic. There are many reasons. Information, as I've explained, is very often in short term. At some point, investors have to calculate their gains and losses. A lot of people would naturally think about how much they have gained over the year. right? It's very unlikely that people would say, oh, average stock return is 11%. More like, that's not how people think, right? When people think, they would say like, well, how much I have gained this year. Furthermore, tax filing is also something that is a natural point of calculation. You have to file taxes every year. And in many countries, you have to state your gains and losses for that year. So people naturally would consider how they are doing in that year. For fund managers, you also have to tell your clients how well you're doing at least once a year, right? Usually more frequently. So that would end up being another reason why you don't want to show poor performance, right? Now, even if the fund manager is very rational, as long as his clients are not as rational, he's still subject to the irrationality of his clients, right? I think a very good movie to watch for behavior that's very related to behavioral finance is the movie The Big Short. That's about the financial crisis, the last financial crisis. And in one scene, the character played by Christian Bale, who is a fund manager, a doctor who turned a physician turned fund manager. He has this foresight, like that the subprime market is going to crash, and he purchased and he was short on those subprime mortgage bonds very early on. The problem is he was so early that he was losing a lot of money on paper. He was losing a lot of money. Well, you have to put up collateral, so he's losing money for quite a bit of time before he earned enormous amount of profit, right? But he was facing a lot of pressure from his investors due to these short-term losses, right? And in the end, he decided to close down his fund after the financial crisis, right? Despite how successful he was, right? So even though you as a fund manager is perfectly rational and you know that in the long run you're going to win, you might not be able to survive the short-run pressure from your investors who are not as rational as you are. Now, so if you like a movie, then The Big Short is a very good movie to watch. It's available on Netflix if you have it. Right. So evidence on loss aversion. What evidence do we have on loss aversion? Right. Okay. The evidence starts with psychology. Okay. Which circle is bigger? And by that, I don't mean these compared to that, right? I'm talking about the one in the middle. This one versus this one. Which one is bigger? Now, whenever you see a question like that, you know it's like a trick question, right? The answer has to be they are the same, right? But I mean, be honest to yourself. I think the one on the left really looks bigger, right? And in psychology, there are a lot of experiments like that. If you take Psychology 101, there are quite a few famous studies, famous experiments that you can do that shows that human perception is relative. This is one of them. Putting your hand into two buckets of water with different temperatures is another one, right? If you put your hand into ice water, if you put your hand into ice water and then you put it into room water in room temperature, right? The water of room temperature actually is going to feel warm, right? So that's another evidence that human perception is comparative, right? So now, if human perception is relative, why would we believe that people would see stock return in absolute terms instead of gains and losses, right? It just seems more natural to think about how much money you earn, how much money you lose versus the absolute amount of money, right? Okay, so what experiments there have been conducted that to illustrate this? So one of the first experiments, and probably one of the most famous one in this particular area, is this one. Okay, so there's an experimenter randomly assigning subjects into three groups. Okay, so now so how do these experiments work? I'm not sure whether you have actually ever paid attention to those type of emails sent out by psychology department, right? There will be typically something like, join like a paid research, right? Come for 2 hours and you're gonna get $50, something like that, right? So this is similar. All these experiments are typically run in university. The subjects are typically undergraduates, right? The difference between economic experiments and psychology experiments is that economic experiments typically pay according to what people do. Whereas in psychology, very often you get a fixed amount regardless of what you do. But the idea is the same. Just find a bunch of undergrads and ask them to do something. Now, there's a legitimate concern of whether you can generalize the result you get from undergrads to the general population, right? So in economics, we do try to see scale up or these studies or bring these studies to the field. Because in economics we really emphasize that you have to give people incentive to do things. Very often studies like these would be conducted in developing countries because their income is lower, right? $1 of research funding goes a lot further in a developing country than in a developed country. So if let's say you run a study in Africa, you can easily run a study that involves a month of salary for people there because the income is low enough, right? But if in US or Hong Kong, there's no way you can do that, right? So this study is with undergrads. So you have 3 groups. To group 1, the experimenter gives them each of them a candy bar, right? So you come in, you sit down, I give you a candy bar. Okay. Group 2, you come in, you sit down, I give you a mug, right? Like typically kind of like a university mug, like CUHK, right? On it. Group 3 comes in with nothing, right? So 2 groups have something in their hand when they sit down. 1 group have nothing when they sit down. Then the experimenter tells the first 2 groups that they can exchange what they have with the other item, right? So if you have a candy bar, you can exchange for a mug. If you have a mug, you can exchange for a candy bar. If you have nothing, then you can choose whatever you want, right? So now, what's the point of this setup? The point is, hypothetically, all 3 groups are have the same freedom. If you can always choose between a mug and a candy bar, right? Because you can always exchange what you have for the other thing, right? So all 3 groups have the same freedom. So if in standard economic modeling, you would expect people's preference to be same in all 3 cases, right? Simply get what you want. If you have enough people, the proportion of people who get a mug should be pretty stable across the groups, right? So people can have the freedom to choose what they want. The only difference is some of them have an item to begin with. Okay. Right. So once again, since people have the freedom to pick what they want, if you expect people to like mugs, a lot of people would get mugs. If you expect people to like candy bars, a lot of people will get candy bars. The interesting thing about this study is that the result is not consistent across groups. Now, group 1, for those who are given a candy bar, most of them, 90% of them, stay with the candy bar. Only 10% of them, 11% of them want a mug. So does that mean people actually want candy bars? Well, for the group of people who were given mugs, 90% of them want mugs and only 10% of them wanted a candy bar. Surprisingly consistent here, right? It's just that it's reversed. What about people who are given nothing? Well, if they are given nothing, it's almost 50-50, right? It's almost 50-50. So this is a paper by Kahneman and Tversky. Two of the most important figures in behavioral economics. They were actually psychologists. They weren't economists. But this study caught the attention of some economists, including Richard Thaler, and that's when the collaboration began, right? Is that they realized that, wait, this is completely inconsistent with what you would typically have in economic modeling, because that implies people's preference changes with what they were given, right? In economics, think about what you have learned in microeconomics. We typically start with utility, or sometimes we start with binary preferences. In either case, we usually assume utility function and preferences to be stable. Right? Yeah. This would be unexpected, that what you want depends on what you were given. Okay. How would you explain that? Now, let's mention the explanation that is given by Kahneman and Tversky, which is the canonical explanation in behavioral economics. It's what we call what happened is, according to Kahneman and Tversky, people get attached to what they have, and when you lose when you exchange, right? It feels like you're losing a candy bar and gaining a mug. One loss, one gain. People don't like that. Whereas if you're given nothing, there's no attachment. No, it's just whatever you pick is a gain, right? So this is a loss and then a gain. People don't like that. For the third group, it's just a gain. People like that. That's the canonical explanation in behavioral economics. And we call it an endowment effect, because you are endowed with something and you get attached to it. You don't like losing it. Right? That's the canonical explanation. Now, can you think of something else? I can think of at least one explanation that you can come up with. Actually, I think there's a very simple explanation. Now, it's troublesome, yes. If you run this experiment in this classroom, you would get very similar results. But I'm not sure it's attachment necessarily, right? It could be just these people find it troublesome, right? Lazy, right? You give me this, I don't care. I don't want to pay the effort, right? So I just keep whatever I have. Right? That's another explanation, right? That's an explanation that should be taken seriously. I would say this alternative explanation is not strong enough to refute all the evidence that we have on endowment effect, right? Because we have run this type of studies with more than just mugs and candy bars, right? We have run them with money, right? So another stuff. So we were just going to take Kahneman and Tversky's explanation that there is an endowment effect. People get attached to things they have, and we just want to see what does that imply. Okay. Right? Endowment effect. Okay. So so interpretation is, if they get the candy bar, subjects who got a mug felt losing the mug as a loss. So lose mug, gain candy bar, not a good deal. Subjects who were given nothing, only gain. So that's great. Yeah, that's the interpretation. Right? So now, yeah, somewhat paradoxically, people in this experiment is the happiest if they were given nothing to begin with, right? They have the freedom to choose whatever they want, right? So, okay. So how is loss aversion modeled in economics? Now, we're going from a psychology observation to an economic modeling, which is very often what behavioral economics is about. We take findings and insights from psychology, which is typically described in words, and we put them in a mathematical model. That's what behavioral economics is about. All right, so how do you model that? Okay, the first thing we have to model, the most important effect, is the observation that a loss should make you very unhappy, right? Much more than how happy you are from an equivalent sized gain, right? So losing $100 is very painful. Gaining $100 is not that happy. That's what we need to model. Okay, this is typically modeled in the following way. You see, this is a piecewise function, right? The utility function depends on some outcome x, and r is a reference point. It's a reference point. So if you want to, you just think about this as money. If you want, like if you have more money than you expect, then your utility is x minus r. So how much you have minus what you expect. If you get less than you expect,
then your utility is phi times x minus r. Now phi is typically estimated to be higher than 1, like 2. So what that means is that, let's say you expect $10 and you get 15, then your utility is 5. You expect 10, you get 5. That's negative 10 because it's negative 2, because it's 2 times negative 5. So an equivalent size gain is not enough to compensate a loss. That's what this model tries to say. Okay. This is estimated by running experiments like the one we had just now with money. Right? Just yeah. We'll see how calculations are done later on. Loss is twice as painful as global gain. Now, we still have to ask, well, what do you expect? Now, this is a tricky question, right? Because we don't actually observe what people have in their mind. How do you know what they expect when they come in? So that's something more tricky. That's something we'll talk about later. Okay, here's another experiment. Now, let's think about what would you choose in this case? Losing $500 for sure versus losing $1,000 with probability half and losing nothing with probability half. Now, one thing you should notice is that the average is the same. Okay, so I'm just asking you whether you prefer losing money for sure or taking some risk, and where you might lose more or you might lose nothing. Now, how many of you would choose the first one? 2, 3, 4, 5, 5, 5, 5. Yeah, something like 5, right? 5 out of a class of about 20 students. That's actually pretty about right? Typically, most people would prefer the second one, right? Although not necessarily as extreme, but more people would choose the second one. Right? That's fine. I mean, people can be risk-seeking. But what about this one? Gaining $500 for sure versus gaining 1,000 with probability or half chance and gaining nothing with half chance. Now you notice that once again the average is the same. It's just that I've gone from losing money to gaining money, right? It's just a flip side of the same numbers, right? Now in this case, how many people are going to take the risk? 1, 2, 2, 3, right? Yeah. So once again, this is very typical. Usually, when you ask people this question, most people would pocket the $500 instead of taking any chance, right? But then this is a risk aversion, right? So one thing that you observe is that people typically risk-seeking when it comes to losing things, and risk averse when it comes to gaining things, right? It's just a matter of changing the wording slightly, right? And you would get this result. If you play with actual money, this will be even stronger. All right, so how do you model this? Right, so you need a utility function in which people are risk averse when they're gaining and they are risk seeking when they're losing. Now, actually, the two seemingly different behaviors is actually consistent with each other. Is that basically what you have is that each additional unit of gain is worth less than before, and each additional loss feels less painful than before. So it's about, at some point, the magnitude is so large that it doesn't feel much. You don't feel much about it anymore. The first dollar that you lose makes you very unhappy because you're getting into the loss territory. But as you lose more and more, at some point you kind of you don't feel as much pain as before, right? You don't feel as much additional pain because you're losing so much already. So this idea that you can basically become less sensitive as you are more further out. It's called diminishing sensitivity. So you kind of basically feel nothing. So how is it modeled? It's typically modeled in a way that you need two different functions for gain, one for gain, one for loss. What you have is you need a concave function that is risk averse in the gain
region and a convex function that is risk-seeking in the loss region. If you draw it, right, so let's say you use something like log, right? If you draw it, it looks like this. Right? But this would not be log because log would have gone to like negative infinity. But this is basically the idea. Now notice that the function is concave on the left and the right hand side whenever you are getting more than you expect. So x minus r is positive. So this is on the right hand side, you're getting more than you expect. Right? So getting more than expected. On the left hand side, this is losing more than expected. So in the region where you're gaining more than expected, you are risk averse. In the region where you're losing more than expected, you are risk seeking. This is simply modeling directly what we observe, right? Without any theoretical reasoning, right? It's just literally drawing a utility function that satisfies what we observe. Right. All right, here's another one. What about this? Let's say you can get $3,000 for sure versus 4,000 with probability 0.8, that's 80% chance, and 0 with 20% chance. Now, if you calculate the average for the second option, that's 8.4 is slightly higher, right? It's 30. The average is 3,200, right? So it's slightly higher, but there's a risk involved. Okay. How many people would go for the second one? 1, 2, 2. Okay, 2. So 2. So a minority. What about this one? 3,000 with 25% chance and 0 otherwise. So this now, unlike the previous case, in the previous case you get a very high chance of getting money. In this case, it's going to be low chance to get money in either option, right? $3,000 with 25% chance and 75% chance of getting nothing. $4,000 with the other option is $4,000 with a probability of 20% and nothing with a probability of 80%. Now, how many people want to choose the first one? No one. Okay. Your answer is very reasonable, right? Look at the second one. I mean, what's the difference between 25% and 20%? But I get 1,000 more in the second case, right? That's kind of the thinking you would have. But unfortunately, I would say, unfortunately for expected utility theory, this is not the way it works in the theory. In expected utility theory, your choice would have to be consistent in the two cases. If you pick the first option in the first case, you will pick the first option in the second case. Right? So this is a requirement of expected utility. Why? Okay, so it's actually not hard to see why. Do I have a calculation here? All right. So okay, so what happens is both pairs involve getting $3,000 at a 25% higher chance. 25% higher chance than getting $4,000, right? The first option always gives you a 25% higher chance. Okay, so it's this when you talk about percentage of percentage, it's a bit confusing, right? So in one case it's 100% chance versus 80% chance, so that's 25% higher. The other case is 25% chance versus 20% chance, that's also 25% higher. Right? That's what I mean. Right? In a published study, 80% picked the 3,000 for sure from the first pair, but only 35% picked the $3,000 for sure. $3,000 for 20%, 25% from the second pair. Okay, so this is not consistent with expected utility. Why? I'm not sure they type it. Oh, okay. Right, so okay, so I somehow I forgot to leave space to do the calculation for some reason. Let's see. Can I actually write it with so little space? All right. Let me try. Okay. So let's say you tell me that you prefer, right? 20% chance of getting $4,000 and 80% chance of getting nothing, over 25% chance of getting $3,000 and 75% chance of getting nothing. This is what you tell me. So what does that imply? What that implies, if you rearrange the numbers, just rearrange the numbers, okay? We can move. Let's see. So I'm going to subtract. I'm going to subtract 0.75 U0 from both sides, right? Then you get 0.2 U4000 plus 0.05 U0 bigger than 0.25 U3000 plus no, that nothing, right? So I just subtract this from both sides. Okay. Now multiply both sides by 4. Multiply both sides by 4. Right? Multiply both sides by 4. Then you get 0.8 U4000 plus 0.2 U0 is bigger than U3000. Right? So this is the first pair of option, right? This is the second pair. So expected utility, by requiring you to make choices based on average utility, means it constrains you to making choices based on ratios. As long as the ratios are proportional, they are the same, right? The proportions are the same. You will make the same choice, right? This is getting $3,000 for sure is 25% more likely than 80% chance of getting 4,000. 25% chance of getting $3,000 is, once again, 25% more likely than this one, right? So yeah, so this is a problem with expected utility theory. It's not a problem with your decision, because your decision, I think most people would agree, is very reasonable. But expected utility theory has this problem where it makes assumption, it has a structure that is not realistic. That's not how people think, right? So right. So what happens in now? One thing you can think about is people really aren't thinking about it in ratios like that, right? What people have in mind is that when you get something for sure, there's a special BB, like this is like it feels like, oh, this is for sure, right? For sure. And if you go from something to for sure to something smaller, even though the ratio is the same, it just don't feel the same, right? So human behavior is full of, you can say it's weirdness, you can say of special characteristics, but human decision is not as straightforward as our economic model suggests. All right, so here's one more. Now, this one concerns cases with very small probabilities, like $5,000 with 0.1% chance versus $5 for sure. Once again, the average is the same, but now I'm asking you to consider a situation where the probability is very small. What will you do? 5,000, right? I think like part of the reason is I think $5 is nothing. So I think a lot of people would say, yeah, let's go for it, right? Like what's losing $5, right? Something like that. But what if it's the other way around? What if I ask you to face a tiny chance of losing a lot of money versus a sure loss of a very small amount of money? $5, right? This is basically an idea of buying insurance, right? Your chance of having cancer, right, is very small. Nevertheless, you might want to buy insurance, right? Because who knows what happens. So it's very reasonable for people to be willing to take a small loss in avoidance of a large possible loss, even if no matter how small the chances. People. Now, the thing is, in this pair of question, what you're doing here when you're telling me, oh, yeah, I probably want to take a small loss instead of facing this chance of having a large loss, you're essentially being risk averse over loss, which is reverse of what I've asked you previously. When the probabilities are not so small, people are actually risk seeking in terms of loss. But when the numbers become so small, people suddenly become risk averse. Right? Once again, human behavior is much more complicated than the simple economic model we used to have, suggest. Right? So, okay, so what happens if you do this with more people, with actual money? About 72% would pick the $5,000 with a small chance. So in a game region, 70% people would take the chance, whereas 83% would prefer the losing for sure from the second pair. Okay. Now once again, I think this is very reasonable. The problem is with our model, not with your behavior. And what you want to think about is what's wrong with the model. What do you think is happening? Like, how do you explain people's behavior? Now, one thing I think you want to consider is how do we even evaluate events that are very rare? Like, even that one is not that rare, right? I mean, it's 1 in 1,000 chance. How do you evaluate something that happens 1 in 10,000 or 1 in a million times? There are plenty of things that happens 1 in a million times, right? Right? Like hit by asteroid. I think that's probably even more than 1 in a million. Right? There are plenty of things like what's the chance that you're gonna have cancer at your age? Very low. What's the chance you get hit by a car if you go on the street? Very low. But it's not zero. Right? So how do you think humans evaluate probabilities that are so small? Right? And if you think about it, a lot of people are not good at math, right? So how do they even think about problems like that? They might not even be able to do the multiplication. So now, experiments like this would not ask subjects to do calculations, right? They would just ask for their gut feelings. We would do that with real money, but we ask for your gut feelings. Just tell me what you think is the right thing to do, right? See what your gut response is, right? What's your instinct tells you. Right? So now what we see is that if you have probabilities that are very small, people's behavior is reverse of what we have just seen. Like so now people are going to become risk averse over loss and risk seeking over gain. Now one possibility is that people actually cannot understand very extreme probabilities in some cases. Now, so if you ask questions like the one we had, and you ask it with different varieties, one thing you will notice is that the probabilities that people use to make decisions seems to be completely accurate. There seems to be some variation like this one. So first, people understand for sure means sure. Like 100% chance, people understand that. No calculation involved. People also understand what it means by zero, typically. Nothing means nothing, right? The difficulty comes in when you ask them to when you deal with probabilities that are not quite zero or not quite one. Right? People are not very good at that. The calculation seems to have some sort of systematic bias. Right? They overweight small probabilities and underweight large ones. Right? So
when you tell people, you know, there's a very high chance, there's a very high chance you are going to develop cancer if you smoke, right? People still behave as if it's not a high chance. Right? But then there are people who worry about things that never happen, like hit by asteroid. Right? In fact, some new research suggests that this line, so this 45-degree line is what would be happening if. So the way this diagram works is this is actual probability. This is what people's behavior suggests, right? So people's behavior suggests that they seem to do not understand probability completely, right? Because there's some systematic deviation with actual probability. Some research suggests that actually the deviation is even stronger at the lower end. Some research suggests that it actually looks like this. That is to say, why don't people understand no chance is no chance? When you ask them to consider situations that happen with a very small chance, they act as if it happens with a much higher chance. I think it's part of the reason it's really hard to think about what it means to be 1 in a million, right? You just act as if there is a chance it could happen, right? 1 in a million, there is a chance it happens. 1 in 10,000, there is a chance it happens. Your behavior might not change that much because the number is so small, it's almost impossible for us to mentally consider what's the difference. Right? So there's some research that suggests people actually behave in a way that overestimates small probabilities until it's actually 0. Then people understand, oh, 0 is 0. Right? I think it's very plausible that that's what's happening, right? So we talk about three properties today, right? Loss aversion. People hate loss more than they like equal to the game. Diminishing sensitivity, that you just losing too much, you don't really feel anything. Gaining too much, you don't feel anything. And then finally, probability weighting, that people don't understand small probabilities that are too extreme. These two components combined, it's called prospect theory. This is the most important model in behavioral economics. It explains a variety of behavior that we can talk about next week. Now, I have to emphasize, this is a theory, right? We can't observe what happens in people's mind. Many of the phenomena that prospect theory can explain, there are also alternative explanations. It's just that prospect theory is one theory that can explain many things, right? So we'll see next week that there are many applications, not just in finance, but also in areas like labor supply and funds and pricing, that suggests that this is a very strong effect. Okay, all right, that's all for today. So again, I remember that you make sure that you can access Blackboard. If you are not enrolled in this course, I can manually add you in to the Blackboard site, right? Yeah. All right. See you next week.
Roughly know where it's turning point.
The
Small probability.
Yes. Yeah. The paper. Yeah. The original paper. The diagram I took. Well. Okay. The diagram I took this paper. The paper I took this diagram from actually I think didn't actually have enough varieties to pinpoint everything. So they fit a parametric curve through something like 4 or 5 varieties. Yeah.
Extrapolation.
Yes, it's extrapolation.
I have a question about the data.
Huh? Yeah.
It seems like with that conclusion, it seems to have nothing to do with W, the original wealth.
Yeah, because theta is a dollar amount. This is CARA. The implication of constant absolute risk aversion is no matter what your initial wealth is, you always invest in the same dollar amount.
Yeah, with the same dollar amount, but later when we came across this, it seemed to be like 30%.
Yes, because because I only have a CRA utility, so it's not completely accurate. Yeah, you should use technically you should use a CRR utility.
So
Yeah, so I'm assuming that the wealth is one to make that work. But yes, to be accurate, you should use CRRA. But CRRA calculation is a lot more complicated.
the conclusion is same.
Yeah, CRRA utility is the same. That's exactly that's the point of Scott's paper in 1985. Is that if you have CRRA utility, you would still have the same problem. Yeah. Thank you.
So a final experiment that I want to mention to you is our fairness study. And so this became a very famous study, and there's now many more, because after we did this about 10 years ago, it became very well known. And we did that originally with capuchin monkeys, and I'm going to show you the first experiment that we did. It has now been done with dogs, and with birds, and with chimpanzees, but with Sarah Brosnan, we started out with capuchin monkeys. So what we did is we put two capuchin monkeys side by side. Again, these animals, they live in a group. They know each other. We take them out of the group, put them in a test chamber. And there's a very simple task that they need to do. And if you give both of them cucumber for the task, the two monkeys side by side, they're perfectly willing to do this 25 times in a row. So cucumber, even though it's really only water in my opinion, but cucumber is perfectly fine for them. Now, if you give the partner grapes, the food preferences of my capuchin monkeys correspond exactly with the prices in the supermarket. And so if you give them grapes, it's a far better food, then you create inequity between them. So that's the experiment we did. Recently, we videotaped it with new monkeys who had never done the task, thinking that maybe they would have a stronger reaction, and that turned out to be right. The one on the left is the monkey who gets cucumber. The one on the right is the one who gets grapes. The one who gets cucumber, note that the first piece of cucumber is perfectly fine. The first piece she eats. Then she sees the other one getting grape, and you will see what happens. So she gives a rock to us, that's the task. And we give her a piece of cucumber, and she eats it. The other one needs to give a rock to us. And that's what she does. And she gets a grape. And see, each of the other one sees that. C gives a rock to us now, gets again cucumber. She tests the rock now against the wall. She needs to give it to us. And she gets cucumber again. So this is basically the Wall Street protest that you see here.